Ladies and gentlemen, dear colleagues, welcome. My name is Zdeněk Hanzálek, and this is the 40th talk of the scheduling seminar. So, believe or not, but we have the seminar already for 2 years, so we have like 2 years anniversary. And today it's 40th talk, right? So let me say a few words about it. So these are the speakers that have spoken up to now. What a nice people we are. I never realized that. We have a nice representation of people from different places in the world, and female and male speakers, and many different topics were treated, ranging from pure math up to the applications and problem specifications. And this is like a little bit of statistics. So up to now, we have had like 27,000 views on YouTube and Zoom. So it means like in average 540 per talk. We have 900 subscribers on YouTube, which is quite a big number. Beside of our email lists, we have like good coverage, I think, in scheduling. And the record in monthly views was like 1,600. The most popular talks per trimester are mentioned here. So we have always like a bunch of 7 talks each season, spring, fall, and winter. So here you see the names of the speakers that have achieved in that particular trimester the biggest number of participants. And here we have some statistics in graphs. So Zoom typically, cumulatively, we have something between 100 and 200-300 of views online on Zoom, which means peak is somewhere around 50, right? Then on YouTube, we have like cumulative numbers in blue and peak in red. So in YouTube, we have less online views, but much more offline views, in, let's say, thousands even. And here you see the number of views per month on YouTube. So we have like from 500 to 1,500 views per month of all our presentations, right? Here on these previous 2 graphs, you have one peak per, or one column per one speaker. Okay, so I think that's enough about stats. I'm very happy that you have joined today, and I hope that there will be more listeners of our seminar. Anyway, we have already a very nice collection of 39, and today we will have 40 different talks on in video on YouTube. So I think it's already some part of scheduling know-how which is recorded for attendee there, right? So, and now please let me ask the speaker today. We will listen to Wojciech Bozejko. He is from Wrocław University of Technology in Poland. He got his PhD from Institute of Engineering Cybernetics in 2003 at the same university. And today he's their professor and head of department of control systems. Beside of that, he plays piano, and he got a master degree from music academies, which is very interesting. He's not the first musician among scheduling researchers that have spoken here. So Wojciech, it's great to have you here, and please go ahead and share the screen and so on, right?
Zdenek, thank you very much. Thank you for this introduction. Today I would like to talk about our works, which takes us previous year. It was connected with our attendance in the project on Wrocław University, Wrocław Center of Supercomputing, and it was connected with the quantum approach to optimization. So we just enter into this subject, and after a year, I can say something from the point of view of scheduling. So for last 23 years, I make some flow shops, jobs, single machine problems, and so on, and some properties, some parallel applications. But now I think this is this moment in which we must interested in this new apparatus and see, is it possible to make something faster or better on these machines. So the subject is optimal solving of scheduling problems on DWave quantum machines. DWave, this is a special kind of quantum computer, and I say something about this. So as you said, I am from the Wrocław University of Science and Technology in Poland. My supervisor of the PhD work was Professor Czesław Smutnicki. So I am from the school of metaheuristics, of tableau search and of such approaches. But now this quantum approach, and we'll see if it is better or not, or a part of this known software tricks to solve our hard problems. So as an introduction, so the concept of quantum computing is from 80s, from Feynman, and nowadays we have two approaches to construct, to design the quantum computers. First one, and this is the most known from the known as general quantum computer, is so-called quantum gate model, and it is made by such names as Google, IBM, Intel, Amazon. So we have a quantum computer with quantum gates, as for example Hadamard gate or Toffoli or other. It works different than the classical one, and mathematicians have many possible applications for this tool. However, a number of existing algorithms for this model is quite few. Everybody knows the Shor algorithms for factorization, or such a or another for finding something in fast time, but to be honest, there are plenty of them. So this is somehow hard to use for computer scientists because of the lack of high-level approach. Programming on the quantum gates looks like as constructing electrical circuits, and it is more close to physics than to modern programming. So the second model, and this is our focus of interest, the quantum annealing as a special kind of hardware quantum computer, and this is developed by two companies nowadays, DWave and NEC. DWave is from Canada and NEC from Japan. So quantum annealing as we can say hardware process of the optimization, very nice fit to the problem of scheduling. And this is nice perspective, but the problem is in programming this machine, because we have to write our problem as quadratic programming problem, QBO, unconstrained or with constraint. Finally, this is unconstrained on the machine, but we can think about it as a problem to be written as at most quadratic programming, so linear also, but there are some problems, and in these problems will be this 1 year we have spent to write our simple optimization things to this machine. So we are interested in quantum annealing, and from the base of in science, from the some axioms. So we have the the system which has an energy, and we would like to make this energy as low as possible. So the way to modeling from the physicist point of view is the Ising or Kubo model, in which we have a Hamiltonian, so-called Hamiltonian, some function which describe the state of some complex system. With spins, with qubits, but finally it is a kind of description of the system which we would like to minimize in sense of energy. And we have some places in which the state is possible to describe, but this is, we can say, quite limited to a class of problems. So the Ising model is from mechanics, and maybe closer to optimization is the same description of the problem, so-called QBO, so quadratic unconstrained binary optimization. Here is not a spin, but just a vector of binary variables and the upper triangular matrix of some data. And such a function can be physically minimized on this machine. So we have such a possibilities to write the problem, and the task is to write our schedule or another optimization task as traveling salesman, vehicle routing, and so on in this language. So our task was just to compute something on this machine and not just describe how to do it. And in this special small problems, there is the whole method. So QPU is an unconstrained model. Somehow, by the way, in this machine, we can write also the problems with constraints, and this can be handled natively in the machine. It is probably done by some Lagrangian inside. We know how to move the problems from as constraint to constraint. From the user point of view, we just have a solver which must be described by a number of constraints and a goal function. So formally, this is unconstrained model, but practically we can use constraints. I will show how to do it. Formally, this is Ising or Kubo minimization of a Hamiltonian function. So, as an introduction, so the main disadvantage of these machines, it doesn't matter is it quantum gate model or quantum annealing model, is that this is not deterministic. It works somehow as a random machine in some sense, but it is very powerful and can give us a very nice result, but without guarantee of being optimal, being exact. So most of papers, we can say, maybe all of them, just describe how to run the problem on the quantum machine, obtain the result, and nothing about, of course, about error. Of course, we can compare it to Gurobi or Cplex and say this is almost optimal, or it is. But inside the machine, we have no way to check if this is optimal or not. This is just a sampler, we can say. So here I would like to propose a method which guarantees such optimality. Finally, it goes to branch and bound method, maybe a little bit changed, but finally the process of describing this from this 1 year ago, when we just start from describing anything on quantum machine and just run, to finally this branch and bound with the upper bound, a lower bound, and so on, computed on quantum machine, it takes us a long time to just program it and run it. So we use this quantum machine as a sampler, and this quantum annealing is just a metaheuristics for us, and it is very very frequently compared to quantum to simulated annealing, because the maybe idea also, but the result is just near optimal solution, feasible or not, but it works as metaheuristic, and we can think about it on this machine as hardware metaheuristics. But finally, we would like to make an exact method. So in opposite to the axiom of these machines that this is a random one, we would like to say that the result is real optimal. So this was the main idea of this research. So we just apply mechanism of branch and bounds. So our lower bounds, upper bounds, and this tree which is cutted as we know. But it is controlled by quantum annealing. So quantum annealing is the way to choose which part of this tree will be expanded. Of course, it doesn't work in parallel. It is a sequential machine, but works as some kind of hybrid. So CPU and QPU as quantum processing unit works not in the same time, but one after one in such a flow process, which ends in a real exact solution. So as a case study, I would like to take a single machine problem. This will be total weighted tardiness single machine scheduling problem. So we have a number of tasks or jobs. We have processing time, due date, and weight of the const function. At standard constraint that machine can perform at most one task in a given time. Task execution cannot be interrupted. We can start all the whole schedule in time 0. So standard 1, also constraint connected with no overlapping. So we have the starting times as a vector of times in which we start tasks. And the constraint that task I must be ended before j or j before I, and starting in positive or 0 values. So standard 1 to describe the single machine scheduling problem. Of course, from the practical point of view, it is nice for us to describe the solution as a permutation. However, on the machine on which we would like to solve this problem, it is quite difficult to write something as permutation. The vector of starting times is more natural, because to obtain this permutation, in fact, we must write some other constraint or making some sorting. So this is not so natural as C++ in C++ or high-level languages. So this vector of starting times is a method of the description of the solution by if we take it to the upper level, to the level of branch and bound, in which we have a set of free tasks and fixed tasks and so on. Better is thinking about permutation. So in our implementation, also this permutation appears. As a goal function, the total number of weighted tardinesses, where this t is a maximum from 0 and completion time minus deadline. So this is just the tardiness. The problem is that this tardiness in the goal function is not fitted to the quantum machine, to this Hamiltonian, in which there is no maximum. This is just sum and multiplication. Any maximal is not possible to write. So this is not so easy to write it in the machine. Somehow we made it so. I will say about it, but in the way of achieving this. So in the very beginning, when we just start, so for instance, such a functions as makespan in job shop, it's quite easier to write in this machine than such a tardiness. So as a final conclusion for this problem definition, we would like to find the optimal order in which tasks have minimal value of this total weighted tardiness. So these machines on which we would like to solve this, they are quite expensive. Such a machine costs about $25 million. But this company, DWave, make a possibility to compute it in a cloud way. So we just have an account, we pay for the time. For our case, it was about $10,000 per year, and it is for half an hour of computing per month. Half an hour, so 35 minutes of processor time of QPU per month. So this is not very big value, and it looks like 70s when on big machines, the time of machine was also quite expensive. So we write it in the as a quadratic programming with constraint. In DWave environment, it's called CQM, constraint quadratic model, and run it by use of so-called lib hybrid CQM sampler. So this is a function. I will show the code, which is executed in one of their machines. Almost all of these machines are in North America. One is in Europe, in Jülich Supercomputing Center, but the rest is in the United States and Canada, mostly in Canada. Los Alamos, the National Laboratory, and NASA, as I remember, bought these machines for the usage, but this DWave just sell it as a time of machine. What is interesting, the processor, which looks here, should be kept in the very low temperature. It is about 15 Kelvin, so minus 200 something in Celsius, and so on. So this is almost zero because of this physical properties of this. Okay, so for formulation this for such a quantum annealer, we have to write it as a quadratic programming. In fact, it is enough to write it in linear form, which is quite natural for people connected with scheduling. So we have the goal function, we have constraints written here, and we have a number of variables. For instance, this tardiness can be written here in such a form that this is just greater than 0 and greater than this real tardiness. So finally, it is taken here to the goal function as the maximal of this, because it must be greater than this one and this one, so greater than maximal one. So as a in branch and bound, as a computing of upper bound of the goal function of the solution, and it is quite natural, but for lower bound this is not. But for upper bound it works quite nicely, and such a model, if we just write it to this machine, compute as a upper bound, because this will be approximation, because we don't know if the result of quantum machine is exact or not. This is just a metaheuristic hardware one, but still without guarantee of the being exact. So we'll write it on the DWave in such a way. The software is given by this company. We have to define the model, define the variables, constraints, objective function, and just this, call this solver. So this is the code in Python. So we define this constraint quadratic model. At the starting times, tardinesses, this X value will be the binary matrix for remember if task I is before J or not. So this is 0 or 1. We add quadratic overlap constraints, and this is only the one in which we have a multiplication of these variables. So quadratic is important here. So for instance, this one, this overlap constraint is taken from this one. This is here, and here we have multiplication of variable s and x. So this is the moment in which this Hamiltonian is real quadratic one. However, we call it. Of course, we can write it in with so-called big M notation without maybe such, but this is easier for this was an easier for us. Also, tardiness constraints, so being greater than the tardiness is greater than 0, and this is great here, greater than 0 and greater than this difference between the completion time and deadline of the due date. Makespan for make this whole makespan is not useful here. However, without it, our schedule can be with some idle times. So to have it move to the left, we use another constraint as such a line to move the whole schedule to the left. Objective function as the sum of weighted tardinesses, and we just define the solver and call them. Finally, the result of this computing, here is the adding this constraint. The final result looks like, just a second, this is still defining of an example, and it looks like this. This is the result of computing. So there is 10 the best solutions in which we have the states of here tardinesses and of here another variables and energy. Energy is this value of this this Hamiltonian, and the lowest one, this is our solution. It can be feasible or not, and it can be optimal or not. So it still works as a kind of metaheuristic, but additionally, classic metaheuristic works with admissible, with feasible solution. It doesn't. It can be unfeasible. So it is sometimes good, sometimes not. So it looks like that. And still, after making this computation and this coding, we have no exact approach. We have a metaheuristics. So for finding this this Graal, we would like to make a kind of branch and bound. So the idea. So an exact hybrid algorithm we would like to propose, and it will be based on classic branch and bound method. For determining the upper bound, we just use this quadratic programming that it was shown before. This is natural form of formulating computing task for this machine. This can be Ising or Cubo, and this can be translated into Cubo. Natively inside the machine, we just write the constraint quadratic model. In contrast, for determining the lower bound, we use the Lagrange relaxation. So we will, of course, this is also, it was 20, 30, 40 even years ago, frequently used in branch and bound to describe good lower bound, if we would minimize something. But the problem was to write it on this machine. So we use the Lagrange relaxation, and this approximation of the value of extremum for Lagrange function will be calculated on DWave quantum computer. So we'll have finally here such a method in which upper bound and lower bound in branch and bound approach is calculated on DWave and as the quantum machine, but the rest of the calculation is done as classical CPU. So this is a kind of such a hybrid in which we swap between CPU on which we organize these computations and QPU on which we just run quantum annealing to have a good upper bound and lower bound and cut these trees, subtrees in the solution tree in branch and bound. It can be imagined in such a way that in classical problem, we have an area of values, we have solutions and cost function. We frequently would like to imagine our landscape of the solutions of the problem, and usually it is compared to white noise and so on, frequent, very many local minimas and so on. So we swap it make a dual problem as a problem of maximization of Lagrange function, and the maximal value we found will be used as a lower bound of the of some subtree of this branch and bound algorithm. So this is rather classical approach, but the way of computing is not classical because this is not, this is made as quantum annealing. So to write this, and this is key point of this work, to write this Lagrange function of DWave, it was a number of problems. So once again, we write our total weighted tardiness with constraints, but we use this big M or big K here notation to not overlap tasks. This is a binary variable for remember if task I is before j or not, positive or zero as k as a big number. And now we would like to make a Lagrange relaxation. So a Lagrange function will use multipliers, real values of u and v. And we will have also the vectors of starting times. Of course, relaxation is based on such an approach in which we put the constraints inside the goal function, so we can use them or not, or make some penalties from not being fulfilled. And the same here, we have the Lagrange function in which we have a part which is just a cost function, so total weighted tardiness, plus penalties for not fulfilled sum of constraints. So this constraint is connected with no overlapping I before j, and this from another side, and some variables. There are plenty of variables because this is n times n, so this is n square variables, constances of some, we can say variables because finally it will be minimized by this numbers, but the number of variables of the problem grows very fast here. Because we use not use constraints, but expand the form of the goal function. So we have such a Lagrangian, and the problem is how to compute it on the DWave. So we transform it, make some order to have one part in which there are only starting times, another in which there are these y variables in which the binary one, and the rest in which there are not si and not y aj, so only these variables of penalties. Of course, we can calculate that. This is just a calculation. This is not difficult, but finally it is important that we divide this Lagrangian function into three parts, and one is dependent on starting times, another from binary variables, and the third is just almost constant, or of course not constant because it depends on u and v, but not from s and y. And now this is the lower bound. Why? Because if we write this total weighted tardiness and write that for optimal solution, it's sum of this part of Lagrangian make the value of Lagrangian lower, because is S with the asterisk is optimal solution. We can look here from the definition. So this is fulfilled. This is positive one. So in fact, we subtract something. So this is a value minus something and minus something. So that's why here is lower than the value of optimal solution of any solution. And finally, we can observe that it works for any value of this Lagrangian multiplier. So in general, we can write here what we want. So finally, we'll have a kind of function in which this should be minimized by some variables. But as we can see in this screen, we can make it for any values of this Lagrange multiplier, so we can take as big as possible. So finally, the best lower bounds for this problem, for using in this branch and this general branch and bound approach, is to make maximization for these variables and minimization for s and y. And this minimization from s and y must be exact. It is very important that it mustn't be approximate, because it doesn't work. It must be exact, but maximization from the point of view on u and v, it is not so important. It works for any values. Somehow here was the very difficult problems for us. It was maybe 8 months ago or something. that we looked that on the DWave machine, we can write something which is minimized or maximized as a minus minimum, but not such subtle problems. So we have here a problem in which we have so-called minimax points. So we have minimization from one variable and maximalization from another. In mathematics, this is called saddle or minimax point. Of course, because saddle, here looks just like this. Yes, this is the saddle, and we have such a point in which we would like to have minimal and maximal. The classic example of such a function as x squared minus y squared, in which we have such a situation. So the result, and this is the main result here, was to written this max min function in right way. And the solution looks like this. We write this in the form of minimization of this Lagrangian function, but write all the additional constraint in such a way to have this part connected with s and y maximal. So, for instance, this part Li will be greater than such a one in which we put here 0, we put here 1, and so on, and all possible values. Of course, the number of constraints will be huge here, but doesn't matter. It just writes, because we have written here that this is minimal from the variables u, v, s, and y, but in fact, from the point of view of s and y, it is maximal because this is greater than all of possible. Similar for this second part with the binary variable. This is on the next screen. If this will be for all possible values of an ij, this will be greater than each possible one. In fact, in practice, this will be maximal. So instead of the formulation in which we have written that this is minimal of something, in fact, this is such a saddle point because this is minimal, but from this s and y, this is maximal. So it was a main result here, I think, that we write such a minimax function as the minimal function and run it on the DWave machine, and it works. Yes, so the test was just by run this. There was also another small problem, because inside this function still we have a tardiness, and as a tardiness, as a maximal function, it still doesn't work on the DWave machine, because it is forbidden to have maximal function. There is only summation and multiplication, no maximal, no minimal. But as we can see in this formulation, when TI appears, for instance, here or here, it is still for some numbers. So we can, during the work of the algorithm, if we add some constraint, we can check the values. So if this is greater than 0, because t is time, and we put here every value, processing time is a constant, deadline is also constant. So finally, we can check if it works or not, and just check if this is feasible here to add one or another constraint. So it was also a trick, but to be honest, this programming of the QPU and of DWave is full of tricks. So to work this, we just have to solve such a simple problems. There is no possible to write max here, what to do. Okay, so finally, we have the hybrid QPU, CPU, quantum annealing driven branch and bound. Quantum annealing driven because we compute upper bound by quantum annealing, and we have a kind of, this is branch and bound with a heap, with such a list of solution to be expanded. So this heap is a priority queue, which is sorted due to the value of upper bounds. So upper bounds as computed as the quantum annealing, and lower bounds also. So this is the, we can say, classical branch and bound, instead of these 2 points in which we compute lower bound on quantum machine and upper bound also on quantum machine. And some experiments, this is very small size because, and it must be spoken that this technology is not yet ready to be comparable in sense of being champion of the algorithms. It can be run for quite big instances, but to obtain, as here, optimality, we can make it up to 10 tasks because of, and I will say in a moment why. By the way, for 7 tasks, as in this case study, 7 factor is only 5,000, but in QPU model, we have almost 10 to the power of 50 solutions. So we can see what is the overlapping of the computation. Somehow it works, so why not? Even if this is a huge number of something inside this machine. So we have an example, and the work of algorithm. This is for 7 tasks. Some iteration, values of lower bounds in the 15 iteration. We have the on the 3rd level of the tree. We have the value of optimal one. I write here that this is in time of 8 milliseconds, and this is interesting thing. If we look, maybe for a moment I will swap inside the DWave panel. So if we compute something on this machine, we have this 35 minutes per month. We have also a possibility to see the timing of problems, and in this cloud approach, if we see the solution, we can see what solver have been. We use the time of computation, constraint quadratic model, solution as previously, and timing. And unfortunately, DWave gives us only 2 kinds of times. One is the total time, and
Yo, wait, I have a question.
Just a second. Probably from the business point of view, this is at least 5 seconds. So it is impossible to run anything faster than in 5 seconds. It takes us only 0.016. So this is 16 milliseconds on QPU, but charging time is 5 seconds. So in month, we are possible to compute only a few hundreds of nodes. So from the practical point of view, this branch and bound doesn't work practically, because we have no time to compute greater number of maybe of nodes. Maybe this is the politics of DWave, that the minimal charging time is 5 seconds. We have spoken with them. They said, no, this is our politics, 5 seconds. This is minimal one. But if we see from the point of no hybrid, just a cloud approach, but from the point of direct run something on DWave, we have some more possibilities. And we can see that these times of processing, of programming are really small. So in fact, every computing we have done on this DWave was at most 30 milliseconds. It was the maximal time of computation, even for instances of thousands. So summary for this single machine total weighted tardiness problem. So we consider an p-hard single machine scheduling problem with the criterion of minimizing the weighted sum of tardiness. We propose exact approach based on branch and bound, which is controlled by quantum annealing. And nowadays, in this problem, we are able to solve optimally solving in the size of n because of the time possible to obtain to compute. Of course, we can use this methodology for our problems in such a kind. For instance, if we have the permutational representation of the solution as travel and salesman. In the second problem, I think not today, because I planned 45 minutes to present it. So for the second problem, we have tried we have also compute greater instances, even to 100 and even to 1,000 tasks. However, for 100, it was possible to compute optimal one, but for 1,000, it was 1 per 10. So it works faster, far and far for instances of the sizes. It works as the approximate algorithm. So we can say that this method is still not comparable to classical one, because on supercomputers we can compute thousands times greater instances, but it grows very fastly. Specifically, DWave is such a kind of machine in which we have the number of qubits up to 7,000, and this is not as in gate model that the error accumulates and so on, that the IBM can compare it, can construct, for example, 127 qubits, and this is problem to make bigger because of cumulative of the error. Here it works as a sampler and works independently. So nowadays 5 or 7,000 it works. So I think this technology will be nice, but it grows, and we'll look for faster machines, because I think the methods are almost ready. Thank you very much.
All right, Wojciech, thank you very much for presentation. And there is one question in a chat, which is 35 minutes per month. So what is the DWave pricing for such an amount of time?
This is $10,000 per year. So we have to divide it by 12. So this is about what is 10,000 by 12? Just a second. So this will
$800.
This is not very much if we compare it to supercomputing cert. Yes, this is 833 for this. So if we divide it by 30, let it be 5 minutes. So this is $23 per minute. So this is maybe not so big, but it grows very fastly if we use it in branch and bound. So this is exponential growth. So still, as such a way is maybe a little bit better, but still, our main goal was not to make a champion algorithm, but to prove that it is possible to run on the approximate machine, on random machine, something which gives a guarantee of the being exact. And this is the main goal, to show that it can be used to compute exact solution without probability. These classes of course, on classes, we have NP-hard problems and so on and so on. In classic machine, they invited some quantum, some spaces in which there is some probability and so on. So this is not for scheduling people. We must have a right answer, yes or no, or some probabilities. Of course, this is important, and there are plenty of approaches connected with such a robust optimization. But this is not this way. In our goal was just check if it is possible to obtain an optimal solution.
All right. There is another question. From YouTube. Thank you for your talk. Have you tried the continuous variables in DWave for the scheduling problem? And
yes.
Or integer variables. I don't know what he meant by.
Yes.
Probably defined as a real number. But how is it about for mixed problems, probably?
Yes, so here in this Lagrange function, the values of the multipliers are real one. And there are two ways. The first one, it works natively on DWave, that we can write that some variable is real one, but if we have a multiplication of real times real, it doesn't work. And we ask to DWave what is the problem, and they were just, it can be real times integer, not real times real. So we skip it in such a way that we program it as in integers and just make a multiplier just times 1,000, divide by 1,000, and so on. So we make a kind of fixed point float values, but using our own arithmetic. So it is possible, but better is to compute on integers and make this real by myself or in such a way.
Okay. So, any other question?
Can I ask a question?
Mhm.
Sure, go ahead.
Sure. So hi, thank you. This is Nasser. Thank you very much for the presentation. I was just, studying about, this DWave company and then, their application in operations research for a while. So what I learned that, it is working for only some certain problems that the constraints have some specific, sort of characteristics that there are, for example, there are binary variables, too many zeros and then some ones, so it works for them for perfectly. For instance, I was working on a sport scheduling problem, as a minimization of break, is a very famous scheduling problem. So I saw a paper, published in Japan. So they claim that the problem, they solve a problem, and the time that they consumed to solve it, it was about 1,000 times faster than my algorithms and then, the mathematical modeling. But what I learned that is they can only solve that, a specific problem. If you add a couple of constraints, even one constraint that, for example, if the two teams are sharing one stadium or just some other simple constraints, then, that solution, that algorithm, and the DWave is just losing its value because, and then it's just advantage because then you cannot solve that problem, efficiently. So I was thinking that it's just only useful for some specific, optimization problems with the, the constraints are such a, specific way. My question is that do I have the right understanding or just, you learn something different in your research?
Yes, so I agree that because during today's seminar, I was the time only for showing the total weighted tardiness, and the borderline for solve optimal such a task was about 10 tasks. So the second problem, I have no time to talk about today about this, but was a kind of knapsack. So this is the problem of maximization of total number of late jobs or on-time jobs. And in such a problem, if we have a representation of binary variables, no the completion time, but just being in the knapsack or not, the sizes of possible to solve instances was much bigger, up to 1,000, and it works much faster. Probably it is because it still is converted into quadratic binary optimization. So finally, this is quite fitted to this binary one. However, classical one, if a single machine with due days or jobs of flows and so on, if we have a variables as the starting of completion time, it can be translated into the language of binary form, because finally the main function which is used to make optimization is this QPU model. So that's why some problems of binary representation, it's works much faster because it is quite easy. Of course, if we look into the possibilities of the machine here, maybe I can show it for a moment on this page of DWave. We can also observe that the number of variables. Just a second, dashboard here is there are machines here. Now, for instance, here we have binary quadratic model here and some description of this is probably somewhere in Canada, and parameters. Yes, now maybe here number of maximum number of variables. This is a million here. Yes, for binary one. For a constraint quadratic model, let us see, number of constraints is 10,000, maximum number of linear constraints, quite huge. It depends, because to be honest, we still don't know where is it computed. Is it on the DWave 2000Q or this advantage system and so on? This is cloud model. But as you say, some problems are more fitted here, specifically this one of the binary representation of something. Such is my view.
So that's correct, because you know, even those people claim that it's just only work for some problems that it has so many binary variables, and then in those constraints most of them are 0, so it works perfect in those areas. It can beat branch and bound, just traditional optimization methods only for those problems, right? Okay, thank you, sir.
Thank you.
All right. Are there any other questions? If not, so thank you very much, Wojciech, for really interesting topic. I have never heard about quantum computers in such a detail close to our domain. And now let me mention the talk which will be presented by Rainer Kolisch from TU Munich in 2 weeks. And he will speak about the resource constraint project scheduling problem with flexible resource profiles, about models, methods, and applications. So looking forward to meet you in 2 weeks, the April 26th. Okay. So thank you very much and bye-bye.
Bye-bye. Bye-bye. Bye.